Hello everyone, this is Anu Agrawal here, and now I'm gonna tell you about the inner product, which is a part of inner product spaces. So first, what is inner product? Let V be a vector space over R, and inner product on V is a function that associates with each pair of vectors U and V in V is a real number, denoted by the inner product of U and V that satisfies the following axioms. The first is inner product of U and U is greater than or equal to 0, and inner product of U and U is equal to 0 if and only if U is equal to 0, that is positive definite. The second one is the inner product of U and V is equal to the inner product of VU, which is called symmetry. The next one is inner product of U plus V and W is equal to the inner product of UV plus the inner product of VW. The next one is the inner product of CUV is equal to C into inner product of U, V. Now the last two properties make the inner product linear in the first variable. And you can see this here. Using the symmetry axioms, it can also be shown that the inner product is linear in the second variable, that is inner product of U, V plus W is equal to the inner product U, V plus inner product U, W. And the next one is inner product U, CV is equal to C into inner product of U, V. With these additional properties, the inner product is said to be bilinear. A vector space V with an inner product is called an inner product space. Let's take some examples. The first is, let V is equal to the matrix containing 1 and 3. Then find all the vectors U in R square such that inner product of U, V is equal to 0, where the inner product is the dot product. Now the solution is, if U is equal to the matrices X, Y, then the inner product of U, V is equal to U dot V, which is equal to X plus 3Y. So that the inner product of U, V is equal to 0 if and only if Y is equal to minus 1 by 3x. Therefore, the set of all vectors such that inner product of U, V is equal to 0 is given by capital S, which is equal to the span of the matrix containing 1 and minus 1 by 3. Now let's take the another example. Let V is equal to P2 with inner product defined by PQ is equal to integration of 0 to 1 Px Qx dx. Then we have to find, the first is, let Px is equal to 1 minus x square and Qx is equal to 1 minus x plus 2x square. Then find the PQ, and the second one is, let Px is equal to 1 minus x square. Then we have to verify that Pp is greater than 0. Here's the solution. The first is, using the definition given for the inner product, we have PQ is equal to integration of 0 to 1 minus x square into 1 minus x plus 2x square into dx, which is equal to the integration of 0 to 1. Now multiply these two factors, we get 1 minus x plus x square plus x cube minus 2x4 dx, which is equal to x minus 1 by 2 x square plus 1 by 3 x cube plus 1 by 4 x4 minus 2 by 5 x5, and the value containing 0 to 1. Now putting these values, we get 41 divided by 60, which comes out to the final answer. Now the part B is the inner product of P with itself is given by PP is equal to integration of 0 to 1 containing 0 to 1 of 1 minus x square dot 1 minus x square into dx, which is equal to the integration of 0 to 1 minus 2x square plus x4 dx. Now integrating this factor, we get x minus 2 by 3 x cube plus 1 by 5 x5 of 0 to 1. Now solving this, after solving this, we get 8 by 15, which is greater than 0. Hence we have verified the part B. Now come to the next part, which is properties of the norm in an inner product space. Let U and V be the vectors in an inner product space V and C a scalar. Then first is norm of V is greater than equal to 0. The next is norm of V is equal to 0 if and only if V is equal to 0. The next is norm of CV is equal to the mod of C into norm of V. The next is mod of inner product of U comma V is less than equal to norm of U dot norm of V, which is also known as Cauchy-Schwarz inequality. And the last one is norm of U plus V is less than equal to norm of U plus norm of V, which is also known as triangle inequality. Now let's take the example regarding these properties. Let V is equal to R square with inner product defined by inner product of U comma V, which is equal to U1 V1 plus 3 U2 V2. Let U is equal to the matrices containing 2 and minus 2 and V is equal to the matrix containing 1 and 4. Then first part is verify that Cauchy-Schwarz inequality is upheld, and the solution is using the given definition for the inner product. We have modulus of inner product of U comma V is equal to mod of 2 into V plus 3 into minus 2 into 4, which is equal to mod of minus 22 is equal to 22. Then the norm of U and V are given respectively by norm of U is equal to square root of inner product of U comma V is equal to square root of 2 square plus 3 into minus 2 square, which is equal to square root of 16, which comes out to the 4. And norm of V is equal to square root of V comma inner product of V comma V. Now putting these values, the values of V1, V2 and after solving it, we get norm of V is equal to 7. Since 22 is equal to mod of inner product of U comma V less than norm of U into norm of V is equal to 28. Thus, the Cauchy-Schwarz inequality is satisfied for the vectors U and V. Now the next is verify that the Cauchy-Schwarz inequality is upheld. Now the solution is to verify the triangle inequality. Observe that U plus V is equal to the matrix containing 2 and U minus 2 plus the matrix containing 1 and 4, which is equal to the matrix containing 3 and 4. So that the norm of U plus V is equal to square root of 3 square plus 3 into 2 square, which is equal to square root of 21. Since square root of 21 is equal to the norm of U plus V, which is less than norm of U plus norm of V, which is equal to 11, thus the triangle inequality holds for U and V. Here we have taken that B is a part, prove that Cauchy-Schwarz inequality is old. So sorry for that, because I have mistaken here. We have to show that triangle inequality holds in part B. So thank you everyone. Similarly, you can take the lots of example regarding these vectors.